a general question for everybody. What can I do to increase my improve my approximation? What can I do with these approximations, Riemann sums? Max, what do you think?
The tangent lines.
Oh, we were just approximating with rectangles, right? So what do you think I could do to improve the approximation, Ryan?
Use more of them.
Use more rectangles.
Oh
Yeah? Okay, so in general, you know, we pick a point and we have like these rectangles and stuff. And if I use more rectangles and I squeeze more rectangles into the space, what's going to happen to the length of our base? It gets smaller, right? So if we get small enough, this rectangle is going to collapse to become basically a line. Right? So it's just like a line. Now, the height of that really skinny rectangle is just the height of that point. So that's x comma f of x. Right? Because of this curve is f of x. And then the base of this really skinny rectangle, we're going to call dx. Because dx is like our differential, like our small little piece of x. So what's going on? There's limits going on in the background. So, and what we're saying is that our area is equal to the sum of f of x times dx, right? So that's the sum of, many rectangles. So I'm doing this in a very non-rigorous way, okay? But I want you to understand the concept, right? So if you have all these really skinny rectangles lined up next to each other, you have like an infinite number of them, well, at the limit as your base goes to 0. And then what happened was throughout history, this S, to denote the sum of all these rectangles, became elongated. And then we had our height times our base. Yes, it should look familiar. Right, exactly. So the integral sign is really just an elongated S. And what it's telling you is that you're summing up a whole bunch of rectangles with height f of x and base dx. Got it? I hope something clicks a little bit here. And then how many rectangles? We say all the rectangles from point A to point B. Right? From point A to point B. And that will give us the exact area, right? The exact area underneath the curve. So the integral sign, the antiderivative, every time you were finding the antiderivative, you are really finding a function that describes the area underneath the derivative curve. Alright, it's pretty cool. That should be really cool. Okay, so how do we use this on our calculators? So let's pick y equals x squared minus x plus 3 again. And let's type that in our calculator. And the calculator froze. Awesome. Oh, okay, we're good. Okay, so right, x squared minus x minus 3. We're going to change our viewing window by graph. Let's see here. Okay, so here's our graph. Okay, so there's the equation. Pick a viewing window that makes some more sense. There's our graph. Once you have the graph, what we're going to do is we hit second calc. And then what number do you think is going to be helpful?
7.
7. That's the equal sign. So you hit 7. The lower limit, so we're trying to find the area from 0 to 3. So you hit 0, upper limit is 3, hit enter,
Oh.
it fills it in,
Sweet.
gives you your answer.
Sweet.
Let's see here. Let's take that, and that's how you do that. And here was our answer, 13.5. By the way, the trapezoid method approximated the area to be what?
14.
14. The actual area is 13 and a half. So the trapezoid method was pretty good with only 3 rectangles for this particular function. All right, the actual integral is much better. Now, keep in mind that even the calculator is approximating. The calculator can't take the limit to infinity. The calculator just takes your widths to be really small, like 0.01 or something like that, and it's able to give you a really accurate approximation. Okay, so you can use that now in physics class. Hopefully, maybe you could use it 45 minutes ago. I don't know. Sorry.
No, I think.
You're
Oh.
welcome.
I'll leave it
All right.
at that.
Yeah, I'll do. I don't know.